Section 7.2 is going to deal with ratios still, but what we call ratios and similar polygons. So now we're going to apply these ratios to similar polygons or similar shapes. Okay, so first of all, what is a similar polygon? Here's the characteristics, and I talked about this Wednesday a little bit. These polygons are going to have the same shape. What that means is they're both rectangles, or they're both parallelograms, or they're both squares, or they're both triangles. Okay? And they're both the same types of triangles, whether they're both right triangles or they're both acute triangles, they have the same shape. But not necessarily the same size. Okay? So similar polygons have the same shape but aren't the same size. Not necessarily anyways. So number one, are those shapes similar? No, because they're not the same shape. This one is a rectangle. This one is a parallelogram. Number two, are those similar? Yes, they're both squares, but they're not the same size. And then number three, are those similar? No, they're both triangles, but one is a right triangle and the other is an acute triangle. Okay, they're not the same shape. So the reasons number 1 and 3 are not similar is because they're not the same shape. Now, we're going to use kind of that concept here to answer some questions about similar triangles, okay, or similar polygons like you see in number 5. So number 4. It says identify the pairs of congruent angles and corresponding sides for triangle ABC and triangle DEF. So in triangle ABC, you have the angles 59 and 35. Okay? If we wanted to figure out the length of that third angle, we could. We don't necessarily need to, all right, because we know both angle B and angle E have to be the same because of the third angle theorem. So the angles that match up, okay, are angle A is congruent to angle D, angle B is congruent to angle E, and angle C is congruent to angle F. So those are the pairs of congruent angles. The corresponding sides then, okay, we can take from the fact that we have these congruent angles, and we just have to match up the segments, all right, that have the endpoints that are the same pairs of congruent angles. So like segment AB, angle A and angle B correspond to angle D and angle E. So what that means is that AB corresponds, okay, to DE. Okay? And then angle A and angle C correspond to D and F. So that means segment AC corresponds to segment DF. And then the last one, BC, corresponds to segment EF. So if you can match up the congruent angles, then that'll in turn help you match up the corresponding sides. Now number 5, identify the pairs of congruent angles and corresponding sides. Again, we don't have a triangle, all right? Instead we have, it looks like a rhombus here, okay? But follow the path of the angles, okay? So angle S is congruent to angle Z, okay? So I'm gonna write it this way. S is congruent to angle Z, okay? Then I'm going to do this. I'm going to write the names of the figures, S and Z, okay? All right, then we have to go the same direction here, okay? Because W and Y have the same values, and so it doesn't really actually matter which way you go, okay? Because P and R and WY, you have kind of two choices, okay? But let's go clockwise, all right? So now moving up to W, W is the same as P, okay? So angle P is congruent to angle W. So as I continue to write the names of the figures, P and W. And then keep going, Q and X match up, all right? So angle Q is congruent to angle X, Q and X. And then the last but not least, Y matches up to R, angle Y is congruent to angle R. Okay. Now, the names of these two quadrilaterals, one of them is SPQY and the other one's ZWXR. Remember, the names, the order of the letters tells us which angles correspond to each other. So we can always use those names as well. Okay, now let's do some math. Okay, I want to determine whether the polygons are similar. And if so, write the similarity ratio and a similarity statement. Find the value of x. Okay, great. So how we're going to determine here whether they're similar, okay, for these two quadrilaterals is we're going to do the following. First, you've got to check the angles. Okay, you've got to check the angles. Are they congruent? Okay, well, if we look at quadrilateral, looks like ABCD, all of those angles there are congruent to angles EFGH. Okay, so yes, ABCD, okay, those angles, I'll put a little angle symbol here, are congruent to angles EFGH. And that'll help us match up the sides. Okay, so check to make sure your angles are congruent. Okay, and then from there, now we are going to move on to the sides. And what I have to check for are the sides proportional. Oops. Okay, are the sides proportional? Okay, meaning this. Okay, if we match up the sides according to the congruent angles, okay, AB and EF, okay, and then BC to FG, and then CD to GH, and then finally AD to EH. So I've matched up the corresponding sides and created ratios with the corresponding sides. This quadrilateral, ABCD, will be similar to quadrilateral EFGH if all of these are equal to each other. And you know, make sure you reduce them. But if they're all equal to each other, then yeah, we're going to have a similar figure. Okay, so AB is 12. EF is 6. BC is 26. FG is 13. CD is 13. GH we don't know. AD is 14. EH is 7. Okay? Now, if you look at this, the ratios where we do have both numbers, okay, they are all 2 to 1. This is 2 to 1. This is 2 to 1. This is 2 to 1. Okay, so what we're going to say, even though we don't know that fourth one, we're going to figure out what x should be in order for it to actually work, right? In order for it to be similar. Okay, since these three ratios are all the same, then yes, it is proportional. Okay, so yes, these two polygons are similar. I forgot to answer yes here, the angles are congruent. Okay, so how we write that we have similar polygons is we use this symbol right here. Okay, that's a horrible representation. Let me do it again. This symbol right there. Okay, so what we're going to say is polygon ABCD is similar to the polygon EFGH. Our similarity ratio is 2 to 1. Okay, that's what we figured out there when we were comparing the sides. Now, the value of x. What we need to do is we need to take the proportion that has x, and we got to set it equal to our similarity ratio. Okay, so let me use a different color here so it kind of stands out. And I can find room. I'm going to do it right inside this first polygon. Okay, so 2 to 1 is equal to 13 over x. We use our cross products, so 2x equals 13. Divide by x, x equals 6.5. That's the value of x. Okay, moving down here to number 7. Determine if triangle JLM is similar to triangle NPS. If so, write the scale factor and the similarity statement. Okay, so first of all, angles. Okay, are the angles congruent? Yes. Okay. Second question. Are the sides proportional? Okay. So let's match up the sides. So if I look at the similarity statement, JL matches up with NP, and then LM matches up with PS, and then JM matches up with NS. Okay, and we're hoping that they're all equal, but we don't know. Okay, so JL is 75, NP is 24. LM is 60, PS is 30. JM is 45, NS is 18. Okay? So those problems right there, okay, or I should say those three ratios, in their most reduced form would be the following. 75 over 24. Does it reduce? Yeah, it does. 25 over 8. Is that equal to 60 over 30, which is 2 to 1? No. And then let's just check the 45 to 18. That will reduce as well to 5 to 2. Okay? So, even though only one of the three, or one of however many sides you're comparing, doesn't work, okay? Don't even really need to check the last one, but they don't work, okay? So, no, these triangles are not similar because their sides are not proportional. Go ahead and turn the page. Up at the top here, we have a boxcar problem. Okay, I'm going to call it that just because it's talking about a boxcar. Okay, a boxcar has the dimensions shown, and then we have a model of the boxcar. Find the length of the model to the nearest inch. Okay, so if we're assuming that these two are similar, okay, we're going to compare the lengths, okay, which this is a length, this is the length, and the widths. This is the width, and this is the width. Okay. All right. So we're also comparing the boxcar to a model. Okay, and now the problem doesn't give us a scale factor. It doesn't give us an order, so then we're kind of free to create the order we want. Okay, but what we know about the boxcar is this. The boxcar has a length of 36.25 and a width of 9. But all the information about the boxcar is in the numerator. Okay, now all the information about the model is going to go in the denominator, but again, all right, here's where order matters. Okay, this first ratio has the lengths, so that's why x has to go here. The second ratio has the widths, so that's why 1.25 has to go there. Cross multiply, and you end up with 36.25 times 1.25 equals 9x. You solve that and you get x is equal to 5 inches. And that's what we were trying to find. Okay, that's the width. Or I'm sorry, that's the length, 5 inches. Okay, scroll down. Okay, all right. Now, we're told that these two quadrilaterals are similar with a scale factor of 3 to 4. Okay? And the order is this: A, B, C, D to J, K, L, M by a factor of 3 to 4. Okay, that's how it reads. Okay, it gives us the lengths of the sides of J, K, L, M. What are the lengths of the sides of quadrilateral A, B, C, D? Okay, so now here's a way to think about this. I'm going to set up my proportion. Okay, here's my scale factor is 3 to 4. Now, A, B, C, D. okay, I don't know what the values are for the sides. So there's where my variable is going to be, okay? All right, and now let's say, first of all, we want to find the length of AB. Well, which side corresponds to the length of AB? Side JK. So we put a 6 there. And we would cross multiply, right? And we would have 18 equals 4x, okay? So x is equal to 4.5. Okay, so that would be the length of AB. Okay, now we've got to move on and find the length of another side. So let's say we want to find the length of AD. Okay, well, which side corresponds to AD? JM. Well, JM is 12. So now, instead of 6, it's going to be 12. So 3 times 12 is 36, equals 4x. X is equal to 9. That's the length of AD. Okay? Well, now we want to know another side. Okay? So let's find the length of DC. Well, which side corresponds to DC? ML. Well, ML is 18. So now 18 times 3, which is 54, equals 4x. So x is equal to 13.5. And that's the length of DC. Okay, and then last but not least, we want to find the length of our last side, which is BC. So which side corresponds to BC? KL. So that means the 15 goes in here now. And 15 times 3 equals 4x. So x is going to be equal to 11.25. And that's the length of BC. Okay. Now, the next question is, it asks, what is the perimeter of the quadrilateral? Okay, well, understand this. The scale factor is the same for the perimeter as it is for the lengths of the sides. So here's what I mean by that. Okay, our scale factor's 3 to 4. Okay, the 3 and everything in the top comes from A, B, C, D. Everything in the bottom comes from J, K, L, M. Even the perimeter. Okay, so the perimeter that we know the perimeter of JKLM, we just would add 12 plus 6 plus 15 plus 18. Okay, so the perimeter of this guy is 51. So if I throw that into my proportion right here, okay, JKLM is in the denominator, so that's 51. I don't know the perimeter of ABCD, that's what I'm trying to figure out. Cross multiply, 51 times 3, okay, equals 4x, and you end up with x is equal to 38.25. Do I have dimensions? Inches. Inches. So that's the perimeter right there. Okay, now area, we're going to examine that in the next problem. Okay, all right, last but not least, we're back to triangles here. Okay, triangle ABC is similar. Again, there's the similarity symbol. Triangle ABC is similar to triangle DEF. Okay, so here's what I know. Okay, I know that BC is 4 millimeters and EF is 12. Now, if I look at my similarity statement, BC and EF, those sides correspond. So I can create a scale factor. And since it doesn't give us order, okay, we can use whichever one in the numerator and denominator we want. Okay, so let's go triangle ABC in the numerator and triangle DEF in the denominator. Okay, so we're going to use the sides BC to EF, which is 4 to 12, and reduce that 1 to 3. So there's my scale factor for the sides and the perimeter. Okay, and I'll jot that down. Sides and perimeter. So if we answer the question, find the perimeter and the area, draw a picture. Okay? Now, I'm going to kind of ignore the directions on draw a picture. Okay? So just bear with me here. Okay? So for the perimeter, okay, my scale factor is 1 to 3. Okay, and again, ABC in the numerator, DEF in the denominator. We're told that the perimeter for DEF is 42 millimeters. So DEF's in the denominator, that's 42. The perimeter of ABC, I'll write it like this. The perimeter of ABC we don't know. Cross multiply and you'll find out. So 1 times 42 equals 3 times PABC. Okay? So 42 divided by 3 gives you 14. So the perimeter of triangle ABC equals 14 millimeters. Okay? Now, area. Area is a little bit different in terms of the scale factor. Okay? Area is units squared. Okay? Just remember that. In this case, millimeters squared. So what we're going to do with our scale factor is we're going to take our scale factor and we're going to square the numerator and the denominator. So it's going to transform into 1 squared is 1, big change there. 3 squared is 9. This is the scale factor for area. Okay? A little bit different than the scale factor for perimeter. You got to square both. Okay, but the order's the same. ABC is still up here. DEF is still down here. Okay, so if I want to figure out the area of ABC, I know the area of DEF, it's 96. Okay, and then I'm going to figure out the area of ABC. Cross multiply. 96 is equal to 9 ABC, or the area of ABC. Okay, and then we got to go 96 divided by 9. So the area of ABC is equal to 10.7 millimeters. And that's it.